So, yeah, hello all. This is our other project that is sand production prediction using machine learning. So here again, we are going to apply machine learning in one of the topic that is sand production prediction. Okay. By the end of this particular session, you will understand the petroleum engineering problem of sand production in oil wells. You will identify key geological and engineering parameters affecting the sand production. We are going to apply machine learning algorithms. We are going to implement many things. Let's see them. Okay. So first of all, let's try to understand the problem. So sand production, I guess you are petroleum engineers, you guys all know what exactly is sand production. Basically, sand is produced while we are taking the production out of our oil wells. So it is a critical problem in petroleum engineering because of this. Many things can happen. It has economical and technical impacts. Okay. So again, let's see how our data is looking like. So we have permeability data, porosity data, compressive strength of the reservoir, cohesion data, frictional angle, grain size, cement quality, clay content, reservoir pressure, temperature, water saturation, perforation density, completion type, flow rate, draw down pressure, oil viscosity, oil density, sand production rate. So the sand production rate is basically our Y parameter that we have to capture basically. Okay, we are going to train different models here: linear regression, ridge regression, random forest, and all. Here again, in this particular project, we had the data with us, but if let's say you want to generate some synthetic data also for that itself, I have provided this particular functionality that will generate the synthetic data based out of the physics on that particular data point. Okay, so you can use this. You don't have the data with you. This generate data thing, calculate sand production is used in this generate data only. In this particular class, production data generator. Now, our second class comes into the picture, that is our sand production predictor. Just give me a second. Mhm. Yeah. So yeah, we'll initialize our machine learning prediction systems here, our models, our scalar, our label encoder, or categorical variable encoding, and best model also that we are going to use. After that, we are going to pre-process our data. We will prepare our raw data for machine learning. A raw data frame will come into the picture, this particular data. Then we are going to do what? We are going to split our data into feature and target variables. Then we are going to do the categorical encoding for the completion type. Completion type is a categorical type of variable, right? So we are going to do the categorical encoding for that here. Then we are going to scale our data. We are using the scalar here. And then our X scaled and Y will be created. Then comes our train model function, a simple function where we are going to train different models. Linear regression, ridge regression, lasso, random forest, gradient boosting, spot vector regression, neural network. How we are going to evaluate it? By 80-20% of train test split. We are going to fit each algorithm. We are going to generate the prediction for train test split. And then we are going to compute RMSE score, R square score, and mean absolute error for each model. And cross validation, we have also applied for robust performance here. You are able to see these are the values that have been calculated, and this is the cross validation score. And then we are going to select our best model, basically the one which is having the highest R square score on the test set. Then again, we are getting the future importance for our model, which features are important by using the red, by using our tree-based models. Okay, so we'll be getting the feature matrix with the column names. Then we are going to plot the results. It will create a comprehensive visualization dashboard with the RMS score, R square score, actual versus predicted values, feature importance, residual plot, and distribution comparison. So all those things will be plotted here in this particular form. Then finally, our print model summary. It will print the complete comprehensive performance report. It will give a performance table for all models. It will give the best model. It will give the key metrics summary, and it will give the top most important features. That thing will be happening here. And this is our main function. The main function again, the orchestrator function that orchestrates the complete project workflow. Starting with the welcome message and setup. Then our data generation will start, but we already have the data, so we can skip this also. Basic statistics of the data generation. Then our ML pipeline will start. Train all the models and stuff. Then our feature importance analysis pipeline will start. And finally, our report analysis, result and report analysis will start. So this is the complete code here. And now let's train the model. Let's start it. Okay, data set we already had. That was not an issue. Then our models have been training. These are our model parameters. Gradient boosting is giving the best R square score. We have a negative R square also for given network. These are the top 10 important features. Permeability is the most one. RMSE error is highest for neural network, lowest for gradient boosting. Obviously, gradient boosting is a good one. Not that much particular good, but good compared to others because we are also getting some negative input. So there is a scope of improvement here in the models. You can improve the models by data stored here. We'll delete these things, well data. Here. We can improve the models by tuning the hyperparameters. But yeah, that's up to you. I'll share the code, play around it. Okay. So that's all for this particular project.